Hey guys, how are you? This is Nikhil Nakka presenting you a new series of lectures, that is GATE 2018 Electrical Engineering Solutions. In this video we will start discussing the questions from power systems topic. This is me, Nikhil Nakka. Read a little bit about me. I'm a freelance professional GATE IES recruitment exam trainer for electrical engineering, freelance R&D engineer, and Indian patent holder and verified educator here on unacademy.com. Okay, today there is an occasion. Today is 15th Feb. So this is the birthday of my dad. Okay, here is my dad riding this yellow bike of mine. And unfortunately, I've lost him 2.5 years back. But I just wanted to share with you that today is his birthday and he means a lot to me. And he is what responsible for what I am today. His words, his inspiration, everything made me the man I am. And this picture actually is a little bit crazy one. It was clicked by the traffic police. Okay, we were driving triple, right? So driving on a bike with three people is a crime. It's out of rule. So they clicked to fine us. This was my dad, and behind him it's me, and the last one is my brother, my little brother. So it's a kind of funny moment. So this is the my Unacademy profile. You can follow me here. I'm a verified educator here. Verified educator means they are among very few of the educators are verified. One of the top educator in India. And see, there is a course for power systems also, and also other courses for electric circuits. Okay, this will be very much helpful for your preparation, exams preparation. Apart from this, many more new courses are going to come. Wonderful courses, like I'm going to plan a new course on MCQs. I will be just discussing about different types of MCQs from all topics in electrical engineering, something like that. So it's going to come soon. So let's start discussing our gate questions. First question of the day: the positive, negative, and zero sequence impedances of a 125 MVA three-phase 15.5 kV star grounded 50 Hz generator are 0.1 per unit, J 0.1 per unit, J 0.05 per unit, and J 0.01 per unit respectively on the machine rating base. Okay, on the machine rating base 125 MVA, the machine is unloaded and working at rated terminal voltage. If the grounding impedance of the generator is J 0.01 per unit, then the magnitude of fault current, okay, is asking you to find the magnitude of fault current for a B phase to ground fault in kiloamperes is up to 2 decimal places rounded off. Okay, so let's write down what is given. He is given the base rating of the system, or base MVA, that is SB, as 125 MVA. He is given that on the machine rating base. Okay, machine rating is the base MVA, and VB will be the system voltage 15.5 kV. He did not mention anything about base voltage. He did not talk anything about base voltage. But why did I assume? Some students might get doubt. Sir, how did you take 15.5 kV as the base voltage? So my dear students, please remember the terminal voltage of the system VT is always equal to its base voltage. Okay, the base voltage of the system is to be considered the terminal voltage of that particular generator of the system. Okay, please keep that in mind. Okay, what is the terminal voltage of the generator? That is only going to be its base voltage, especially while discussing about these kind of problems. Okay, so the terminal voltage here, okay, is 15.5. Therefore, it is only the base. So whenever you know the base MVA and base voltage, immediately find out the base current. Because you are supposed to find the fault current, you need to know base current first of all. So IB can be found by this relation, because base rating SB can be written as root 3 VB into IB, right? Because it's a three-phase system. So from this relation, you can find out what is IB. So base current, by solving, I get 4.65 kiloamperes. Okay. So usually VB kilovolts and IB will be in kiloamperes, kilo into kilo, and SB will be in MVA. So that is clarification regarding the units. Okay. So, and what else is given? He's given the values of all these impedances. Okay, positive, negative, zero, and Zn is the neutral impedance. Okay, so he's mentioned that it is LG fault, isn't it? What kind of a fault is this? B phase falling to the ground. So it is an line to ground fault. Now let's write down what are the relationship for line to ground fault current relation. So in a line to ground fault, okay, please keep this in mind. The fault current equation is defined like this. Okay, IF is equal to 3 into E Z1 plus Z2, okay, divided by Z1 plus Z2 plus Z0 plus 3 Zn, and in fact this should be plus 3ZF also. Okay, plus 3ZF also. Please make this a note. What is ZF? ZF is the fault impedance. Okay, impedance introduced by the fault. And what is this E here? E is the pre-fault voltage. Okay, pre-fault voltage, that is the voltage of the system just before occurrence of the fault. Okay, just before occurrence of the fault, what was the healthy system's voltage? That is what the pre-fault voltage. And always keep in mind, and I suggest you to just go through my videos on fault analysis. I've already made some videos on fault analysis, and I've also discussed some problems. In that I will be describing a procedure how to attempt the problems, especially in fault analysis. So basically the calculation, the fault analysis, the topic itself involves, or the majority of the questions involves or asks you to find the fault current. That is the main aim, finding out how much fault current is there. So the entire calculation goes in per unit system, because usually your impedances will be given in per unit. So whatever currents you obtain also will be in per unit. Therefore, everything should be in per unit. Finally, when you are presenting the fault current, convert it into actual values, if depending upon the question. Okay, in the question, if he is asking you to just present in per unit, you can present in per unit. If he is asking you to present in actual, then you have to go for actual. But here you see in KA, in kilo ampere, so he is asking in actual. So do the procedure in per unit and then convert into actual by using this base current. So we will see how that also we will be doing. Okay, so ZF is the fault impedance. Here there is no fault impedance. So in this particular given question, so he did not talk anything about fault impedance. Therefore, ZF equal to 0. And then we will substitute the values. Okay. So by substituting the values, okay, this is what you get. Okay. IF is equal to 3 into 1. Um, 3 into 1.1. Okay, this is Z1, Z2, and Z0. 3 into Zn. So some people might get confused. I have taken E for 1. Okay, there is no mention about E. What is E? Is it 1 per unit, or what is the per unit value of E? But I have taken 1. So guys, I have already discussed about these things in my previous videos. Okay, just in my videos of fault analysis. When the system is unloaded, always the E value, the pre-fault voltage should be always taken as 1 per unit. Always should be taken as 1 per unit. So that also let me clarify. Voltage per unit. Okay, E is nothing but the per unit voltage. So what is the per unit voltage? Basically actual voltage by base voltage. You agree with this? What was the actual pre-fault voltage before occurrence of the fault in the system? 15.5 kV, no? Because he is telling the machine is unloaded and working at the rated terminal voltage. Okay, actual voltage of operating is the rated terminal voltage. What is the base voltage? 15.5. So what is the per unit voltage? 1 per unit. So that is what E is. So that is how you got. When the system is previously loaded, then it will be the different. So I have already discussed how to proceed if the system is earlierly loaded. You just go through my videos, that will be much helpful. So now it is unloaded. So most of the questions will be getting an unloaded model only in GATE exam especially. And solving this, I will get IF is equal to 3 by 0.19, and that gives me the per unit fault current as 15.789. Okay, so what should I do next? I got the fault current in per unit. I need to convert it into actual. So what relation should be used? So this is the relation. I actual, okay, is equal to I per unit into base. Why? Per unit is equal to actual by base. Using that relation, I got this value for I actual. So per unit into base. 73.41 kiloamperes goes your right answer. Okay, hope you understood. Let's take the next question. Consider a lossy transmission line with V1 and V2 as sending end and receiving end voltages respectively. Z and X are the series impedance and reactance of the line respectively. The steady state stability limit for the transmission line will be some options given. Okay. So we will understand certain things. Lossy line. What do you mean by a lossy line? Lossy line, you call it when the transmission line, you are adding the resistance also. You are considering the resistance present in the transmission line, because many a times in most of the power system problems or power system analysis, it is a common practice to neglect the resistance. We approximate the line by neglecting the resistance. There are two main reasons for neglecting the resistance in usual analysis. One reason is normally the line reactance value will be much higher than compared to resistance. That is the main case. So, you know, Z is equal to R plus Jx. So if X is much greater than R, you can make R equal to 0. You can neglect it. So it doesn't affect your accuracy much. And second reason is by eliminating R, you are going to reduce the complexity of problem. Okay, mathematical operations complexity is going to reduce, so you can finish your analysis in a relatively lesser time. So there are the two main reasons why we usually approximate by neglecting the resistance of the system. And then was talking about steady state stability limit. So steady state stability limit is nothing but the maximum power that can be transferred by that particular transmission line. Okay, under what conditions you define stability, steady state stability, that we will discuss in some other lectures. But for now, you have to remember steady state stability limit is equal to the power max that can be transferred. So this is the generalized expression for maximum power that can be transferred through a transmission link. V1, V2 by B. You know, a transmission line is defined by its A, B, C, D parameters. Okay. So V1, V2 by B. Do you remember what is the unit for B? Ohms. Okay. And unit for A, what is the unit for D? These two guys are no units, whereas C has a unit of mho. Please keep this in mind. Okay, hope you might have known all these things. V1 V2 by B minus AV square V1 square B cos beta minus alpha. Okay, so this is the actual equation for maximum power that can be transferred in a particular transmission line. Actual equation means when you are considering even the resistance also. Okay, when the line is lossy, you can say when the line is lossy, when means no approximation has been made. Okay, and generally for an approximate model, the case is R will be equal to 0, isn't it? Then it is called as loss free line, because resistance causes a line loss. That is the reason you call it a lossy or loss free line. And A will be equal to D equal to 1, therefore alpha equal to 0. What is alpha? Alpha is the angle of A, because ABCD parameters are actually complex numbers. Again, B is equal to Z. You know, B is the unit of B is ohm. The ohmic part of the transmission line is nothing but the B. And Z is equal to Jx, because there is no resistance. And beta will be equal to obviously 90. C will be 0. What is C? The admittance component, or the Siemens component, the shunt branch component. Usually we also neglect the shunt branch or the shunt capacitance in the particular transmission line. Okay, because the value of shunt capacitance also is very high. So like that we will be neglecting it. So this is the approximate model. Okay, or you can say loss free model. So when you apply all these conditions here, okay, when you keep B is equal to Jx, beta equal to 90, A equal to 0, finally what you get P max as V1 V2 by X. Okay, this is the P max of a loss free line. Now you compare both of these equations. Now tell me which is higher or which is less. The power max under lossy condition is less as compared to power loss under loss free condition. Therefore option B goes the right answer. Less than the, what is this, V1 minus V1 V2 by X, loss free line, isn't it? So that is the answer. Hope you understood this problem. So let's take the next question. Consider a two-bus power system network with given loads as shown in the figure. All the values shown in the figure, okay, are in per unit. The reactive power supplied by the generator G1 and G2 are QG1 and QG2 respectively. The per unit values of G1, QG1 and QG2 and line reactive power Q loss respectively are. So let us understand this given problem. Okay. So basically there are two generators like this. Okay, there are two generators over here, this G1 and G2. G1 and G2 both are generating complex power. It means it is generating both active and reactive power. Active power, reactive power, active power and reactive power. And they are connected to two buses. Say this bus is bus number 1. Say this is bus number 2. To the same bus, load is also connected. Okay. To the same bus, load is also connected. And these two generating stations are joined by a transmission link having some impedance of or reactance of J0.1. So impedance or reactance is nothing but it is an inductor as shown here. Definitely it will consume some reactive power. Therefore some reactive power loss also will takes place. Okay. Now we will see the power equality relations here. So the basic drama of power systems is to satisfy the load. Okay, the entire power system, entire generating stations, why do we place? To supply that electric load. So anytime the power generation must be met with the power demand. Pg must be equal to Pd. So what is the generation present in this given system? Pg1 and Pg2. Okay, active power at generator 1 and active power at generator 2. What is active power at generator 1? 20, at generator 2 it is 15, isn't it? And what is the demand basically? Demand means what is drawn. In a real-time power system, the power demand will be power divided by the load as well as the power lost in the transmission line resistance, because that is also an active power loss, I square R loss. Basically here there is no resistance in the transmission line, therefore P loss will be equal to 0. However, you see P1 is 20 and this is 15, and PD1 is 15 and this is 20. So power generated is equal to power demand, no problem here. Now you see at QD equal to QD, QG is equal to QD. Similarly, generated reactive power will be equal to the demand of reactive power. So generating reactive power, where is the reactive power generated? The two generators are generating the reactive power, QG1 and QG2. And who is consuming these two loads? Okay, J5 and J10. This is the amount of reactive power consumed by the two loads. And even this transmission line consumes, that is Q loss of reactive power. So this is going to be the equation. Okay, QD1 plus QD2 is 15. That's how we got this relation. Okay guys, so let us assume how the active power is actually flowing here. Now just look at this generator 2. This generator 2 is generating a power of 15, but the load connected at this bus, okay, bus number 2, is consuming an active power of 20. That means 15 is coming from here and remaining 5 must come from this transmission line, right? Now you look at here, generator 1 is generating 20 megawatt. Here 15 megawatt of power is being drawn into this line. That means remaining 5 megawatt or 5 per unit power is flowing in the transmission line. So my final conclusion is, okay, power in the transmission line. Power in the transmission line. How much? 5. Okay, active power. I'm just talking about active power. So what is the power relation for a power going in a transmission line, power transmitted by a transmission line? That is P is equal to V1 V2 by X sine delta. Many of you are conversant with this formula. V1 is the sending end voltage, V2 is the receiving end voltage, X is the reactance of that line, sine delta. This is the delta angle, isn't it? We need to find the delta now. What is the power transferred? 5. We will just put down all the values. We have 5 into 1 into 1 by, this is 0.1, right, given here, into sine delta. So this becomes sine delta is equal to 0.5. And what does it yield? Delta is equal to 30 degrees. So we found the value of delta. Okay, we found the value of delta. How much is there? Delta 30 degrees. Okay, so this is a little bit about the active power. Now let's talk about how the reactive power is being managed, or how reactive power is flowing in this particular system. See, it is generating some reactive power of Qg1, and when the G1 is generating some reactive power of Qg1, out of this Qg1 amount of 5 is being drawn by the load, and remaining reactive power here is sent into the line, say that is Qs, sending. And what is Qs equal to? Qs equals to Qg1 minus how much? Minus 5, isn't it? Minus 5. Or I can say Qg1 is equal to Qs plus 5. Please keep this in mind. Okay. Now, this Qs, after dropping here as Q loss, a reduced Qr will be receiving at the bus 2. Okay, will be received at the bus 2. And at the bus 2 load is connected, it is drawing a reactive power of J10. As well as generator is also supplying from here a reactive power of Qg2, isn't it? So I can write from these relations here QD1, what is that? QD2, sorry, QD2 or 10 units of reactive power, right? So 10 is equal to Q received plus Qg2. From this, Qg2 is equal to 10 minus Qr. So we will just keep these equations aside. Okay, they will be helpful once we finish finding out the other things. Okay, now we will write down the equations for, or we will find out what is the Qs and Qr. So the moment you know Qs and Qr, you can find out Qg1 and Qg2. That is what asked in the question, right? And you are also required to find the Q loss, isn't it? What is the Q loss? You see, Qs is being sent, Qr is received. In between, Qr is lost. Q is lost. So Qs minus Qr. So the moment you find both Qs and Qr, your entire problem is solved. Now let's find out what is the Qr. I request you to please keep in mind or remember these equations for Qr and Qs. In some other special video, I will discuss how did we arrive at that solution. Most of you will be conversant with this equation of QR, but QS will be quite just a little bit difference. Okay, so little bit opposite will be there. So let me write down. So QR will be equal to V2 by X into V1 cos delta minus V2. This is the equation for QR. Similarly, for Qs, it will be V1 by X into V1 minus V2 cos delta. We just keenly observe what is the difference between the QR equation and Q2 equation. Okay. So the nomenclature might be different. So most of you might know this equation by this relation that Q is equal to V by X E cos delta minus V. Okay. Just the difference is for E is nothing but will be taken as sending end voltage here V1. V will be equal to V2. That's it. That is the only change, nothing else. The nomenclature is different. Okay. So just don't get confused by these things. Okay, so let's substitute the values and then we will find out. Okay, so what is V2? Magnitude of V2 is 1, magnitude of X is 0.1, V1 1 into cos delta. What is cos delta is 30, this is 0.866. Okay, 0.866 minus V2 is 1, so 1 by 0.1 is 10. So finally you will get answer as minus 1.34 per unit. Similarly, you substitute the values here, 1.01, then it becomes 1 minus 0.866. Then this becomes 1.34 per unit. So you got the value of Qs and Qr. Okay, Qr is minus 1.34 per unit. This is 1 plus 1.34 per unit. Put down these values in all those equations, then you will find out the answers. So just put it in Qg1 equation. Qg1 equal to Qs plus 5. What is Qs? Qs is how much? 1.34, right? 1.34 plus 5, that is 6.34. Now Qg2 is we have to find. Qg2 is 10 minus Qr. 10 minus what is Qr? Minus 1.34. So it becomes 10 plus, right? 11.34 per unit is going to be the QG2. And then Q loss is what we require. So Q loss is QS minus QR. QS is 1.34 minus of minus QR, right? So this become both plus. So it becomes 2.68 per unit. So I cannot go back into the previous slide. You just scroll back the video and you can find out the option which is appropriate to these values. Okay, so this is the way we solve this. Let us proceed to the next question. So in this question, the positive, negative and zero sequence impedances, okay, of a three-phase generator are Z1, Z2, Z0 respectively for a line-to-line fault with fault impedance ZF. The fault current is IF1 plus is equal to K into IF, where IF is the fault current with zero fault impedance, and the relationship between, okay, ZF and K is. Now what is the type of fault here? Line to line fault. Okay, it is a line to line fault. For a line to line fault, I hope you remember the sequence diagram. Okay, the sequence diagram, you will have only the positive sequence and negative sequence. Because the absence of ground, there will be no negative zero sequence. Okay, so this is the positive sequence source E1 and this is the positive sequence impedance Z1. Okay, and then you might have a fault impedance ZF which is connected to another reactance, and this is the zero power bus. This is Z2. Okay, this delivers a current of I2, okay, or say IA2, which is zero sequence current, negative sequence current. Here the current is IA1. Okay, from here IA1 current is current, positive sequence current, and the voltage at this point will be the positive sequence voltage VA1, and the voltage here would be VA2. Okay, this is the sequence network for, okay, this is a sequence network for a line to line fault. Okay, and you see how the fault currents are included. So zero sequence current will be zero, but positive sequence current, okay, is equal to the negative of the, and positive sequence current and negative sequence current are both equal and opposite to each other. So these are the relationships. I hope you have to remember these fundamental things. Okay, so from this we can write down what is the equation for this particular system. Okay, the equation for fault current in this system would be, no, just let me erase off this thing. So this is going to be your equations, okay, for fault. All right, so IF is equal to root 3E. The reason why did we take root 3 is just to, E is the phase voltage, so I am just converting it into line. So like this, so root 3E Z1 plus Z2. In fact, there should be ZF. ZF is considered to be 0 because IF is the fault current with zero fault impedance. Is already given in the question. Therefore, I am neglecting. But IF1 is when fault impedance is also considered. So you have seen the previously the network diagram, and from that you can write down this equation quite easily. So the given relation is IF1 is equal to K times of IF. I am just putting down the values of IF and IF1 like this. So root 3E get cancelled, and then we can solve this subsequently. How do we solve it? So I just wanted to find the ZF value. So I will do something and I will put ZF on one side, remaining things on the other side. So what I will do is now Z1 plus Z2 by K is equal to Z1 plus Z2 plus ZF. Like this I can rewrite this equation. From this I want to find only ZF. So ZF equal to Z1 plus Z2 by K minus Z1 plus Z2. So from this I can write K into Z1 and then all those things, mathematical equations, and then finally you get this is the answer. ZF equal to Z1 Z2 1 minus K by K. So what is the answer? Option A is the right answer. Okay, hope you understood how did we do this. So and then next question, or the last question I can say, the series impedance of a matrix, series impedance matrix of a short three-phase, okay, it's a three-phase line, three-phase transmission line in phase coordinates is ZS, ZM something. Okay, what is ZS? ZS is called as self impedances. While ZM are mutual impedances. So what are the self impedances and mutual impedances? Basically, you consider a three-phase transmission line like this. Three-phase transmission line, three phases. So every transmission line has got its own, every line conductor has its own impedance called as ZS. So ZS is the self impedance of each line. And it is also assumed, or it is believed, that between these both lines there will be a mutual impedance called Zm. Between these two lines again a Zm. Yeah, between again these two lines we have a Zm. Yeah, between two lines we will have mutual impedance. So that is how you related here. So why did we consider like that, and how is it helping us? We will see those things later. Okay, in some other video, I'll make a special dedicated video for that. So for a transmission line, you have to remember this very important thing. Basically, this question, this model question is the first time in GATE exam so far. So for a transmission line, its positive sequence reactance equal to the negative sequence reactance or impedance, that is equal to its ZS minus ZM. Please keep this relationship in mind. Okay, you are finding out the positive and negative sequence components of impedances using the actual ZS and ZM values. And zero sequence impedance will be equal to ZS plus 2ZM, ZS plus 2ZM plus 3Zn if neutral impedance also considered. Here Zn equal to 0, you can neglect that, but I am just writing ZS plus 2Zm plus 3Zn. So just by looking at these both equations, what you can say, the positive sequence impedance equal to the negative sequence impedance, both are the same. Basically for a static device this follows. Okay, whereas for a rotating device this is going to be different. The positive sequence is going to be higher than the negative sequence impedance. So when you talk about a motor or alternator, something like that. And you look at the zero sequence impedance, it is high, right? It is higher than the positive or negative sequence impedance. So Z0 will be very much higher than this positive sequence, or what again you say, negative sequence impedance. How many times high means? 3 to 4 times. Okay, this 3 to 4 times, and Z0 is much higher than Z1 is Z2. Z1 is equal to Z2. This forms a very important objective for some PSC exams, other competitive exams. Okay, so what do we do now? So what else is given in this line? He has given the value of positive sequence, isn't it? Positive sequence and zero sequence impedance value is also given. Z1 is given and Z0 is given. Say this is equation 1, say this is equation 2. I just want to subtract Z1 minus Z0. Okay, Z1, okay, 1 minus 2 I am doing. So when I am doing this, ZS minus ZM, minus ZS minus 2ZM, this becomes 0, right? There is no whispering about anything about Zn. Nothing was described here. So then it becomes minus 3Zm. Okay, and then from this Zm will be equal to Z1 minus Z0 by minus 3. Then that becomes Z0 minus Z1 by 3. You know the value of Z0, you know the value of Z1. Just subtract it. You will get 3 plus J21 by 3. So that is finally equal to 1 plus J7. And in the question is asking the imaginary part of Zm. Okay, what is the imaginary part of Zm? See here, J7, 7. So your answer is going to be here 7. Okay, hope you like this series. I'll be continuing the same manner for other topics also, especially from this GATE 2018 paper. So finally guys, thank you for watching this video so patiently. It's been around half an hour. So don't forget to subscribe to the channel for more awesome videos. Like this video if you liked it, and share with your friends, anybody who is preparing for exams. Comment your opinion, any suggestions, anything is welcome. I will reply and respond to you. Finally, have a nice day. So do these things before I do my next video.